Okay, so this talk is about some special cases of the Bloch-Kato conjecture. So let me start by telling you what that conjecture says. So the context for the conjecture is we have V, which is a geometric p-adic Galois representation. Which for the purposes of this talk just means that this is it appears as a subquotient of some étale cohomology group possibly with a Tate twist for some, let's say, smooth projective algebraic variety over Q. It could be over a number field, but let's just stick to Q. Okay, and so to such a thing, you can associate an object called the L function. So this is a function of a complex variable defined by an Euler product, where the local factors, at least I'll write them down when L is not equal to P. When L equals P, you should do something different. The local factors look like this. So you're taking the characteristic polynomial of Frobenius on the Scholze representation, plugging in L to the minus S. Now, a priori, that might look like it's not clear why that's totally well defined, because the characteristic polynomial would have QP coefficients a priori, and this is a complex number, so you have to make sense of this. You can do this by just sort of brutally choosing an embedding of QP into the complex numbers, but it won't really matter because at least for primes of good reduction, the eigenvalues of Frobenius are, of course, all going to be algebraic numbers. So really, for all but finally many primes, this is actually a polynomial with algebraic coefficients. Okay, so that's the L function. And the conjecture about it is that if you, well, first of all, a priori it converges when the real part of S is sufficiently large. The first part of the conjecture, which I won't write down, is that it has a morphic continuation to all of C, and then that the order of vanishing at the point S equals 1 equals this sort of more arithmetic quantity, which is the dimension of the Bloch-Kato Selmer group, minus a correction factor dimension of the Galois invariance. So the Selmer group, I won't write down the definition in full detail because it's not really so important for this talk, but it's defined as the kernel of a map from the global Galois cohomology to the product over all L of this kind of thing. So in other words, you define some local subspace of classes for all primes L, and you're looking at global Galois cohomology classes so that when you restrict the decomposition group at each prime, it lies in your prescribed local subspace. And so for when L is not equal to P, these are just unramified classes, and when L equals P, you have to do something with p-adic Hodge theory. So the conjecture is that this sort of kind of arithmetic object attached to V, its size is exactly predicted by this analytic L function. So to give you some orientation, like what are some kind of known examples or cases? So the first example would be when V is a trivial representation. Then the L function is just the Riemann zeta function, and you can check that in this case, so it has a pole at S equals 1. You can check the Selmer group vanishes, so you get -1 on both sides, so that works. And in fact, it is also known for any one-dimensional Galois representation. And so the sort of next interesting case would be if you take an elliptic curve over the rational numbers, and you look at the p-adic Tate module of this elliptic curve. If you apply this construction, so the L function that you get for this elliptic curve is actually just the L function of E. So the conjecture is then that the order of vanishing at S equals 1 of the L function for the elliptic curve is just the same as the dimension of the Selmer group, which is the usual Selmer group that people study for elliptic curves. So in this case, you recover BSD modulo the relation between the Selmer rank and the actual group of rational points. So the Bloch-Kato conjecture you should think of as some kind of vast generalization of BSD that's supposed to work for any geometric p-adic Galois representation. So beyond these sort of, oh, I'm sorry, I forgot to state what's actually known about this case. So it's known. So Bloch-Kato is known here when the order of vanishing of the L function is at most 1. So this is due to the work mostly of Kolyvagin and Gross-Zagier. And Rubin for the CM case, and maybe except for a few sort of bad primes, but it's mostly known. And even sort of a lot is also known about the other direction when the Selmer rank is at most 1. But beyond the case, beyond sort of the rank 0 and 1 situation, there's really almost nothing known at all. And that's sort of the template for what's known about sort of more complicated cases. So first of all, this story with elliptic curves actually also works for any V that appears in the cohomology of a modular curve. So those would be Galois representations for weight 2 modular forms, not just the ones attached to elliptic curves. You can do this exact same thing there. And also for higher weight modular forms, there's work on this as well. And so beyond that case would be when V is more than, well, there's sort of recently started to be cases known, some sort of more recent examples when the dimension of V is larger than 2. So I don't want to attempt to give a comprehensive bibliography of these because I'm sure I'll leave something out. But what I think, what sort of I want to say in general about these examples is that they all kind of combine ideas from the GL2 case, so the elliptic curve case. With kind of with sort of special or specific methods sort of for each new case. So in each new case that's known, there's kind of some very special geometry or some special underlying automorphic story that gives rise to this V, and then sort of you need all the ideas for elliptic curves and then more to kind of specialize to each particular situation. So what I'm going to tell you today is about some particular new example where some things are known about Bloch-Kato. And again, as you know, it will always be in rank at most 1, sort of keeping it with what we know in general. But sort of the parts of what I'm going to say, so most of what I'll actually say in the talk will really apply sort of more generally than the context in which I'll state it. And sort of most of what I explain will have to do with the themes that sort of arose already for GL2, but I'm going to try to stick to this kind of one concrete setting. So the setting that I'll actually be discussing is Galois representations that appear in the cohomology of a Shimura variety called the Siegel threefold, which you should think of as a moduli space for principally polarized abelian varieties of dimension 2, plus some kind of level structure. The level structure won't play too much of a role, but it depends on this K, which is a compact open subgroup of the finite adelic points of GSB4. So this is called the Siegel threefold classically. And I think this is kind of a natural class of V to look at, sort of beyond the elliptic curve case, In some sense, I think this moduli space is the next natural case from the modular curve, which would be moduli space for abelian varieties of dimension 1. Okay, so we're going to try to say something about Bloch-Kato for these particular V's. But first, I want to tell you a little bit more about what the cohomology looks like in general. It breaks up in this very nice way that is Mingjia mentioned in her talk. It's sort of a general story for cohomology of Shimura varieties. And I'm putting in a Tate twist in the coefficients for some convenient normalization reasons. But yeah, so this cohomology group has not only the action of the Galois group, but also an action of a Hecke algebra of level k. And you can think of this in two ways. So one, this is the Hecke algebra of functions on GSP4, the finite adels that are k by invariant. So it's acting by some convolution. You can also think of it in the moduli interpretation. It's acting by correspondences that keep track of all the different ways that two abelian varieties could be isogynous to each other. So all the different degrees and shapes of isogeny that you could have, analogous to how for the modular curve you have the classical Hecke operators that keep track of degree n isogenies. Okay, so you can decompose the cohomology with respect to these two actions. And it turns out that the only Hecke modules that you get are of this very special kind. So all the Hecke modules come from the finite parts. So this is not finished. I'll finish that line in a minute. They come from finite parts of automorphic representations of GSP4. And before I go further, I want to remind you what that means. So the space of automorphic forms on GSP4 or on any group is the space of nice functions in some appropriate sense on the adelic points of GSP4 modulo the rational points acting on the left. We're looking at complex valued functions. So such things are called automorphic forms. And there's an action on this space of the adelic points of GSP4 by right translation. So an automorphic representation is defined as an irreducible constituent of this space with respect to that adelic action of the group. And any such, which is usually written pi, can be written as a restricted tensor product of sort of local components, where each pi v is an irreducible admissible representation of GSP4 of QV for all the different completions of Q. And so to return to what's going on here, so this decomposition into finite and infinite parts is with respect to that tensor product. And the only automorphic representations that you actually see are ones where pi infinity, actually, okay, just to make sure this is completely correct, let me look at the interior cohomology. So throw away any boundary information. And the only ones you'll see are where pi infinity belongs to a particular discrete series L packet. So there's just one L packet that contributes to this cohomology. And so these are the Hecke modules you get, where this means the k fixed vectors, which naturally carry an action of the Hecke algebra. And they appear with some Galois representation, which I'll call v pi. And so what do these v pi's look like? Well, let me make sort of an automorphic assumption that pi is not cap or endoscopic. And if you don't know what those words mean, it doesn't matter at all. You should think of them as just meaning that v pi is four-dimensional and irreducible. Otherwise, it would be smaller. It would either be smaller or reducible. And so the most non-degenerate thing that can happen is this case. For this implication to be totally true, you want p to be at least 3, which I'll want for other reasons anyway. So okay with that. So these are sort of the most interesting representations that you can see in the cohomology of GSP4. And they all are going to be symplectic. So the Galois action preserves a symplectic form. I'm also going to assume that pi has trivial central character. That's like the center of GSP4 acting on this representation acts trivially. And under this assumption, I can, these will be self-dual, meaning if you take the linear dual and you Tate twist by 1, you get back v pi. It's kind of an arithmetic self-duality. And the reason I put this 2 here is so that things would be normalized to make this true. OK. So all of these v pi's are geometric Galois representations for which you can ask about the Bloch-Kato conjecture. So, I mean, you might think, well, this isn't really projective, so are these really geometric? But because these are sort of all coming from the interior cohomology, they'll also appear in the cohomology of any compactification. It doesn't really matter. These are geometric. And the so first result, which should be on the archive very soon, is that, well, so assume that there, so this is some kind of technical condition, there exists a prime dividing the conductor of pi such that pi L is type 2a. I'm not going to write down what that means, but it's a particular kind of local representation of GSP4 of QL, which you should think of as being the simplest kind of ramified representation. So it's quite similar to in the modular modular form case, asking for there to be a prime with Steinberg or square free level. Okay, under that assumption, the conclusion is that for all but finitely many primes, you have Bloch-Kato in rank 0, meaning if the L value is not 0, then the Selmer group, so that means order of vanishing is 0, then the Selmer group, as predicted, is trivial. And here I should point out that this L value, so v pi depends on p, of course, because it's p-adic, but this L value is actually a global thing. So this is actually what's called the spin L value of pi, and I'll just normalize this to also be 1 for convenience. But so this is really a global thing to have the L value be non-zero, and the conclusion then is something local about all the different Selmer groups. Okay, so that's the statement. Let me just sort of say out loud, sort of a relevant previous result in this direction was the work of Loeffler and Zerbes, who were able to prove something similar, actually for more general kind of weights of these pi's, but only for ordinary primes. And in this setting, it's not known if ordinary primes exist at all, or what their Dirichlet density might be. So, not assuming ordinarity is a good thing. It's very explicit, yes. I could tell you all the conditions. P should be unramified, so pi p is unramified. Also, there are some explicit elements that need to be in the image of the residual Galois representation, which should also be irreducible. Okay. I also want to tell you about a statement related to the rank 1 case of Bloch-Kato. And for this, I want to explain sort of a general idea. And again, so this is something that is relevant far beyond the special setting of this GSP4 Shimura variety. The idea has to do with constructing canonical elements in the Selmer group. Okay, so let's again take X to be any smooth variety over the rational numbers. There's an operation called the Abel-Jacobi map that takes in a cohomologically trivial codimension R algebraic cycle on X. And it outputs a class in well, let me start with just the Galois cohomology, a class in Galois cohomology valued in the 2R minus 1 étale cohomology. And okay, so what's going on here? Like ordinarily, the realization of such a cycle would live in H2R étale. There's some spectral sequence that means if it vanishes there, you instead get a class here. And actually, if you assume X is projective, then it'll definitely land in the Bloch-Kato-Selmer group. Maybe you need some kind of assumptions locally at P, which would be fine in our setting. Should be 0. So the analytic rank is 0, so the Selmer rank should be 0. The order of vanishing of the L function is 0. Yeah. But yeah, thanks for asking. So to use this for our V pi's, of course you want X to be the Siegel threefold. And to get classes in the right degree, this should be H3, so R should be 2. So then you want to ask, well, can I think of any nice codimension 2 cycles here? So those would be curves on this threefold. And in fact, there's a very kind of interesting family of such. If you take B to be any indefinite quaternion algebra over the rational numbers, you can attach to this a quaternionic Shimura curve, which I'll write as XB, which is a moduli space for principally polarized abelian varieties of dimension 2, plus an action of a maximal order in B, plus a level structure. So these are the classical quaternionic Shimura curves. And you can see that as long as the level structures are chosen compatibly, there's going to be a natural forgetful map where you just forget the OB action but remember the underlying abelian variety. So this gives you a sort of quite interesting family of cycles. And if we want to apply this Abel-Jacobi construction, well, sort of your first difficulty, which turns out to be not so bad, but sort of encounter this problem, that XB might not be cohomologically trivial. So that's just kind of a fact of life. It usually won't be. But this is not serious, because if you look at the H4 étale, where this would naturally lie, and you localize at the maximal ideal of the Hecke algebra that corresponds to pi, this will be 0. And here I mean in a characteristic 0 sense. So just localize at the characteristic 0 Hecke eigenvalues of pi. This will vanish. And so in particular, you can kind of think of this whole Abel-Jacobi construction locally. So if you look at the Chow group of codimension 2 algebraic cycles, and sort of extend scalars to QP bar, and then localize the Hecke eigensystem, this will be fully cohomologically trivial. Right? So then you can just sort of get your local Abel-Jacobi images localized at M pi. And so these will lie in sort of the pi part of the étale cohomology. So that would be an H1Q, and then you'd get pi f k tensor v pi. And actually, you can check that they'll land in the finite part because of some purity for this Galois representation. And so, in particular, this gives you some way to construct Selmer classes. And the second theorem is that so under the same assumptions as above, and again, for all but finitely many primes, if this construction gives you anything non-zero, then the dimension of the Bloch Kato, and it gives you anything non-zero for any b that you care to pick, then if there exists a b such that this is non-zero, yes, then the conclusion is that the Selmer group has dimension 1, meaning in particular it's generated by this class, right? So if this is non-zero, you have something in the Selmer group, and then the content is that's actually the whole thing. So this should remind you, if you're familiar with Coley-Vaughan's work on elliptic curves, right? Like as soon as you have a non-zero Selmer class coming from a Heegner point, it generates the whole Selmer group.
Are there examples where you can expect that this is not zero?
Computationally, maybe, I don't know. But what I was, this segues well to what I was going to say next, which is that this is something where you expect, you expect some relation between this xb and derivatives of L functions, which makes this theorem then consistent with Bloch Kato. So there's sort of a conjectural Gross-Zagier type formula in this situation, which tells you that the heights of these kinds of xb's in the Chow group should be related, or Chow group sort of after you localize at pi, should be related to the derivative of the L function of the Galois representation, or equivalently of pi. Then this says for all but finitely many primes, almost every p. So yeah, under the same conditions as theorem A and with the same assumptions on p that I'm not writing down. Yeah. Okay, so yeah, so even if this were proven, it wouldn't directly sort of imply that this derivative being non-zero actually gives you a non-zero Abel-Jacobi image, because there's some issue about non-degeneracy of Abel-Jacobi maps. But at least it's kind of suggestive it should be related. It's not known to be injective in this setting, no. Okay, great. So I want to tell you about sort of the methods involved in proving this theorem, which, as I said, actually until the very end of the talk, will be also in methods involved in proving the GL2 case and other sort of higher rank cases that were known before. And sort of all of the novelty of the proof of theorem A, unfortunately, will be squeezed into maybe the last 2 minutes or something. But I think it's quite interesting to see still sort of the rough outline, hopefully interesting. So the proof strategy, and I'm going to explain everything for theorem A, although the ideas used to prove theorem B are certainly related, closely related. So sort of either of these theorems is really about giving an upper bound on the Selmer group, right? And there's sort of only one game in town for bounding Selmer groups, and that is to produce ramified Galois cohomology classes. So this is the idea of Euler systems, and sort of every known kind of bound on Selmer groups that's ever been proven, to my knowledge, comes in this kind of way. So in this setting, to be a little more explicit, I want you to first pick a Galois stable lattice inside V pi, and then set Tn to be this kind of torsion quotient, mod p to the n. And so the whole game, really, of proving theorem A is the following. So what you really want to do is produce Galois cohomology classes, not for all of V pi, but just for Tn, where Q is, so these are indexed by Q, some auxiliary primes, satisfying some kind of congruence conditions mod p to the n. So I'll just say out loud that these conditions are about what the eigenvalues of Frobenius look like on Tn. They have to be of a special shape. And given these classes, so what these classes are supposed to satisfy is first, when you restrict them to the decomposition group at a prime L, which does not divide either the conductor of pi or Q, they should be unramified, or crystalline if L equals P. On the other hand, when you restrict them locally at Q, they should be ramified, at least under the assumption that the spin L value is not 0. So they're ramified classes in this very kind of special and controlled way that all of the ramification is at this one prime. And so what just to say in words, sort of what roughly you do with these classes once you have them, there's some kind of Poitou-Tate duality argument, which shows you that if you have too good a supply of classes like this, there's sort of no space for any unramified classes. So you can prove this. And so, of course, producing these kappa of Q's is sort of the, it's not so obvious how to do it, and that's where the content of the theorem mostly is. So let me tell you kind of first how they're constructed, and then I'll try to say a little bit about why they're ramified. So these kappa of Q's, you construct them in a very geometric way. So we're going to take G prime to be an inner form of GSP4 that's ramified at Q and at a prime dividing the conductor. And the reason you need it to be ramified at 2 primes is there's some kind of parity obstruction, where if it were only ramified at 1 prime, it would be compact at infinity. And if we ask for ramification at 2 primes, on the other hand, it'll have a Shimura variety. So it'll be kind of split at R, and it'll have a 3-dimensional Shimura variety, which you should think of as sort of related to the Siegel threefold in the same way that quaternionic Shimura curves are related to the modular curve. So some kind of like twisted or ramified kind of form of the Siegel threefold. Okay, so the proposition that you need is that, in fact, there exists a map from the integral étale cohomology of this guy, even surjecting onto our Tn for sort of under the conditions on Q. And the reason this is kind of a remarkable fact is that there is no map from here to T pi. So the reason for that is that there's some kind of Jacquet-Langlands phenomenon where the automorphic representations that you see here are all going to be ramified both at Q and at this L0. And because Q is auxiliary, it's not a ramified prime for pi. In particular, pi won't appear here. So there's no map in characteristic 0, but there is a map mod p to the n. And so this proposition is reflecting some kind of level-raising congruence between pi and automorphic representations that are ramified at Q. And I'm not going to probably explain the proof of this proposition, but it's not trivial. They're admissible primes.
Okay, this is different conversation.
No, it's the same over here, but these are actually not Kolyvagin primes. These are admissible primes. I mean, I can tell you the eigenvalues of Frobenius should be like Q1 alpha and Q over alpha, where alpha is like not it doesn't lie in a certain finite set. Shouldn't be 1 Q. Yeah, there's some condition like this. Yeah. And yeah, so under this condition, such level-raising congruences are sort of possible, and the proposition is that they actually happen in this concrete way. So the idea then is to sort of mimic the construction of the canonical classes in the statement of theorem B, but now on this auxiliary Shimura variety for the group G prime, and then use the proposition to then get Galois cohomology classes valued in Tn. And sort of the first step of this looks good because these quaternionic Shimura curves still live inside this thing as before. There is a moduli interpretation under which you can sort of easily see this, but you can also just think of it as a G-spin 3 group inside a G-spin 5 group. GSP4 is the same as G-spin 5. So n is sort of constrained by q, because q has to satisfy some condition mod p to the n. Yeah. Okay, so of course you then sort of are yearning to take the Abel-Jacobi image. The problem is that now in this setting the fact that xb isn't cohomologically trivial becomes a little bit more serious. So this is where a theorem that's very relevant to this workshop is being applied, called the torsion-vanishing theorem. And let me sort of state it in this very concrete setting first, and then I'll say something a little more general. So under some kind of genericity assumption on M pi, which will be satisfied for all but finitely many p, the étale cohomology of this auxiliary Shimura variety, now with integral coefficients, localized kind of in an integral way at the Hecke eigenvalues of pi, vanishes for I not equal to 3. So this theorem, this genre of result originated with Caraiani and Scholze in 2017. They later refined that in 2019, and it was sort of further refined. And so far, this is all in the context of unitary Shimura varieties, so not actually in this setting. So this has been further refined by Koshikawa and Santos. But then sort of relevantly to this actual statement, this was proven by Xiying Li and Linus Hamann. And actually, Xiying gave a talk about this at this workshop last year. So they proved this kind of statement in PEL type A and C, which includes this Shimura variety here. Yes, I'm being a little dishonest. So if you didn't take M pi, I'm also sort of in practice only using ones that are non-Eisenstein, so it doesn't matter. So that then this like equals the interior cohomology. But yeah, for the actual theorem statement, there's vanishing below middle degree for regular cohomology and above middle degree for compactly supported. So you have to combine them. Yeah, exactly. Yeah. So what this lets you do is then sort of finish the construction. Wow, I can even, this is so convenient. I can even like use what's already on the board. Now, sort of before inverting P, but after localizing at M pi, the Chow group is cohomologically trivial. And so in particular, you can take Abel-Jacobi images and then using the proposition, you can interpret these Abel-Jacobi images as elements of Galois cohomology valued in Tn. And just to like reflect for a moment on the role of this theorem, if you lived in a world where this theorem was never proven, it would really be impossible to construct these in a sensible way, because you would have to, you would know that this cohomology group was, H4 was torsion, it's p torsion, but you wouldn't have a bound on the sort of amount of torsion, and so this would sort of be totally useless. So it really is, sort of, if you had to multiply by an arbitrary power of p, you would lose sort of all relevant geometric information about this class. So yeah, it's sort of being used in a very crucial way to construct these Galois cohomology classes. And in terms of the conditions that I said we wanted on the cohomology classes we produce, well, as long as you make your levels hyperspecial away from bad primes, the fact that these classes will be unramified locally is no problem. What's trickier is proving ramification. So of course, that's still sort of the whole, if these classes aren't actually ramified, you haven't actually produced anything. But so what you still have to do, that there exists some B such that the Abel-Jacobi image of this class is ramified at Q. And it has a chance to be ramified at Q because this whole construction was ramified at Q, but you don't know a priori that it is. And actually, it's really in this step that sort of everything novel about this theorem actually happens. So it's really in the relation of ramification to these Abel-Jacobi images into L values that sort of the hard work actually mostly appears. So I want to give you just kind of a very rough sort of schematic look at how this goes. Actually, let me do it on a fresh board. It's exactly to get ramification, yeah. So if you could think like, what if instead I added level at Q, but stuck with GSP4? Those classes you actually don't expect to be ramified. Sort of the reason is that because T pi is there, it kind of the map that you get to Tn, yeah, it's a little bit subtle to explain exactly, but somehow because of the congruence. Because T pi is still there, you won't get the ramification. It's only because T pi kind of goes away that then these more ramified things have an opportunity to sort of manifest. Yeah. So roughly the relation of ramification to L values looks like this. So you have some information over here about an L value, and you want to relate it to the ramification of a class that you've constructed in this way. And okay, so a priori these are living in really different worlds because this is like analytic and this is like actually in, you could kind of think of this as somehow valued in z mod p to the n or something. So the first step of the relation is to sort of compute this ramification in a geometric way. So this calculation goes back to Yifeng Liu, who sort of first came up with a general framework to compute ramification of Abel-Jacobi images in this way. And there's sort of a recipe where you look at the special fiber of the Shimura variety at Q, which is not smooth, but it has a semi-stable model. And so you can kind of calculate quite explicitly with the weight spectral sequence and come up with some expression for exactly what this is. And in this case, what the answer looks like is it involves some SO3, SO5 periods for the Jacquet-Langlands transfer of pi to a compact G spin 5 group, inner form of GSP4, ramified at L, so compact at infinity. Ramified at L0, which was this other prime where G prime was ramified. So the reason G spin 5 turned into SO5 is that pi is trivial central characters. This descends to SO5. And the sort of reason this G spin 5 group appears in the calculation is that it appears in indexing the irreducible components of the supersingular locus of the special fiber. So you can, so the supersingular locus is sort of purely two-dimensional, and you can sort of, when you sort of do this calculation, you find that to get the local ramification, you have to sort of intersect your class on the special fiber with all the different irreducible components of the supersingular locus. And the shape of what you get is some kind of period, depending on the B that you chose. And so then this is sort of a more arithmetic thing, because this is a compact, this group is compact at infinity. And by the way, I should mention this kind of change of group phenomenon first appeared from the modular curve. It's kind of a very well-known story in that context, where different quaternionic Shimura curves, if you look at their special fibers, you'll kind of see the quaternion algebra changing in variance locally at the prime for which you're taking the special fiber and at infinity.
So there's two arrows. Does this mean there's an explicit formula? Like, okay. Dual PTN, or is it just a qualitative thing, one side?
There's sort of a map. There's like a map in one direction, where like there's like a map from here, from like where this is living to Z mod P to the N, where. So yeah, it's sort of like. Yes, there is an equality in Z mod P to the N. Yeah. And then the relation between those kinds of periods and L values, it then sort of uses much more automorphic things, uses theta lifting from SO5 to half integral weight modular forms on SP4. And I'm not going to go into the details of that process, but I would want to mention that sort of roughly what happens is this L value is related by the Rallis inner product formula to some kind of theta lift, and these periods appear in the Fourier coefficients of that theta lift. And in this process, you lose control of B. So in this step, essentially because it's the same sort of reason that if you have a modular form that you know is non-zero, it might not be obvious which Fourier coefficients of it are non-zero. So that's kind of where you lose track of B. So yeah, that's all I want to say about sort of the shape of the proof. But I want to leave you with a question, which I definitely don't know the answer to. The question is, besides this kind of torsion vanishing and Abel-Jacobi math, are there other ways that perfectoid methods can be used to produce global Galois cohomology classes? So I don't know what the answer to this question is, but I think if you have any thoughts about it, I think they'd be interesting to me and certainly to lots of other people as well, because of the sort of potential relation to bounding Selmer groups and sort of relation to Bloch Kato conjecture from Galois cohomology classes. Sure. But yeah, I'm just like I think sort of one thing that's kind of like perfectoid methods are sort of often like kind of local in nature. Here you can use them to do something globally, and I think it would be interesting to know more examples along those lines. So, thank you.